Okay, looks like I'm recording. All right, so we're going to take a look at assignment number 4. So I'm going to click on our assignment, and these are going to be the problems that I picked for you to do from the end of the chapter. Okay, so so the first couple problems are going to be problems that would pertain to the beginning of the chapter as we looked at it. So 2, 6, 8, 16, and 18 are all problems that would have been earlier per our first lecture. And then the last 4 problems are going to be what we looked at in terms of the second part, or the relative acceleration. So I'm going to open up. And the first problem that we have here is problem 7.2. And it says we have a high performance vehicle, has a 0 to 60 miles per hour time in 8.3 seconds. Determine the linear acceleration of the vehicle and the distance traveled in reaching 60 miles per hour. So this is just going to be using those variables, determining what that acceleration is. So if we look at our equations that we have here on our equation sheet, you're going to focus like in this area right here. Okay, it's kind of standard straight line acceleration problem. Any questions on that? Make sure that all of these problems, if there's an equation, which all of them are, make sure you write your equations in variable form first. Put your units and your values in all phases of the problem, cancel, combine as needed, and then make sure that you identify your variable you're solving for. So in this case, it says determine the linear acceleration of the vehicle. I need to see an A is equal to your number with the appropriate units. Don't just put the number with the units and put a box around it, because I want to know what you're calculating for. I want to know what that variable means. Identify it, label it, okay? The next one we have is 7.6. Starting at rest, a cam accelerates uniformly at 750 RPMs clockwise. Determine the angular acceleration of that cam. Okay, so angular acceleration is that alpha. So this area, okay, it's going to be what you need. Our next one, the angular velocity of a shaft is increased with constant acceleration from 1,000 RPMs to 2,500 RPMs clockwise in 20 seconds. Determine that angular acceleration of the shaft. So kind of using that very same area here to determine that. Then the next problem, homework problem you have is 7.16. The link that they're referring to here is up at the top of the column on the next page, okay? They want you to determine the total linear acceleration of points A and B when this is rotating at a constant clockwise rate at 300 RPMs. So earlier I mentioned when we have a constant angular velocity, that means that we are not speeding up or slowing down rotationally, okay, rotationally, but we still have acceleration because we're changing direction. So there'll be a normal acceleration component at each one of these, but not a tangential. Okay, so just a normal. For problem 7.18, using that same link above with the same dimensions, in this case, we are going to be decelerating at 800 radians per second when we're going at 300 RPMs. Determine the linear acceleration of each one of those points. Each one of those is going to have a normal and a tangential, but then you need to find the resultant of those two, okay? So the total acceleration, when we're just interested in one individual point, the total acceleration is going to be using Pythagorean's theorem once you determine your tangential and your normal for each one of those points and using Pythagorean's theorem to get that value, okay? Now, once you get the magnitude, you also have to know direction. So that's why you're going to have to draw this link out so you can show the angle or the direction that it's at, okay? Questions on those two? Right. Then turning the page, your homework problem is going to be 7.26. This is this compressor link right here. We had strategically done 7.28 so that you have a good example of process for this problem up here. Okay, so there are some differences in the rotational speed and such. So same process, same diagram, it's just going to be some different numbers. So that's number 26. The next one that you have is going to be number 34. Number 34 is the hacksaw we see above here, okay? So you want to, using the relative acceleration method, to graphically determine the linear velocity and linear acceleration of the saw blade. So the saw blade is out here, it's attached up here. So this is going to be a slider going horizontal. This is just like the slider crank mechanism up here for that piston compressor linkage, okay? Except a different application and different values. So that's number 34. And then your last one, number 38, again, we strategically did number 39 as our practice problem. So this was our practice problem here. The angle is different though, okay? So that theta is 90 when we did it for 39. The theta is actually 40 for the problem you're going to do. So it's not the exact same orientation of the kinematic diagram, but most of the sizes are the same there, okay? So then you have the process then that you used for 39 to do number 38, okay? So right now, does anybody have any questions? Look, do I have one more? Oh, do I have 42? That's a homework. Okay, I'm sorry. Let me just check back. Yep, number 42. Oh, good. You get to do another one. So nice. So this is another homework. I didn't mark that one. So this one is looking up at the illustration up here. This is the landing gear. We've looked at that one. I don't know that all the dimensions are the same, so I would use what's here, you know, as your values. And then the landing gear actuation, the small, it's going to be rotating counterclockwise at 15 RPM and accelerates at 4 radians per second squared. Use the relative acceleration method to graphically determine the angular velocity and angular acceleration of the wheel assembly. So over here is the crank side. This is going to be your input. That's going to be the 15 RPMs going counterclockwise. And over here, the wheel assembly is going to be what you need to determine the angular acceleration and velocity for it, okay? So this would be your link number 2, link number 3, and then link number 4 would be your output, okay? So this setup is also similar because it's a, you know, crank, if you would, as that last problem that we did. All right, so that should take care of the homework. Are there any questions? All right. So notice here, I want to let you know, I know these problems get quite involved. You'll notice that some of them are worth 5 points, some of them are worth 10 points, and then the ones that are the relative acceleration, I gave you 20 points for each of those because they're pretty long. Okay. I want to make it worth your while. Doesn't feel like 10 points is enough. Okay. So the rest of the time this evening, you are going to have available to work independently, to work on whatever homework you need to, or making progress on here. I am going to stop the recording. Oopsie, I'll just stop the recording. So I'm going to stop the recording.